All right, in our last video, we looked at programming the warp drive unit, with this ACME Mark IV warp drive controller. And kind of like our parting thought is that, to control any hardware is that it comes down to manipulating, bits, in these registers. So we asked the questions, how do you manipulate bits in memory? Individual bits. It's easy to think about how do you write something, a whole value, but what if we want to manipulate, bits in memory or in these registers? So what we're going to talk about here is, kind of how you do this. And I can guarantee you that if you can walk away here and get a good understanding of what's in this video, there isn't any hardware you can program, because every piece of hardware and every microcontroller, you just use bit manipulation. You can write your own drivers and you will no longer be reliant on someone else's code, on some example code. You can do it yourself and understand it. So the first operation we're going to look at is setting a bit. So I have kind of an imaginary register right here. And what I want to do is set bits 0 and 2. So remember, we're going to list the bits starting at 0, going like this. It's a 0-based index. And so we want to end up at the end of the day, with a 1 there at bit 0 and a 1 at bit 2. But we don't want anything else to be modified. Now you might say, oh, this is easy. Well, why don't you write the hex value like 85 and you're done? Well, that makes the assumption you know what the value is before you start it. In most cases, you don't. That register might have, other stuff, in those other bits going on that might change without you knowing about it. So we got to figure out a mathematical operation to go from the top to the bottom there. So I want to introduce the concept of a mask, or what's called a bit mask. All a mask is another binary number or another number of the same length of your input register. But anywhere where you want to modify a bit, you set it to 1. All right. Now, all we have to do is think about, what operation do we have to do, between the mask and the register to get these bits set. So you might look at this and originally think, oh, it looks like if I add, all right, 0 and 1 is 1, 0 and 1 is 1, all right, and all these are 0 and 0, 0. You go through here, 1 and 0 is 1. This works. Well, there's 1, and I'll scratch out these digits here. Let's say we already have a 1 here, and we want to we put our mask as a 1 there. A 1 plus a 1 is a 0 with a 1 carry. So adding doesn't work. So let's think about another operation. Okay, you look at AND. All right, that doesn't work because 0 ANDed, 0 ANDed with 1 isn't 1. So let's think about bitwise OR. By bitwise OR, what I mean by bitwise is you take every bit in every column and OR them. This 0 ORed with 1 is 1. 0 ORed with 0 is 0. 0 and 1 is 1. All right. Notice what is, in this case, 1 ORed with 1. Let me erase this one, is 1. We get rid of this goofy bar or carry. All right. And that's correct. That leaves that bit set, so on and so forth. So setting bits is ORing, logical OR, or I'm saying bitwise OR. In C code, we do a bitwise OR with the bar, and we just say the register, and we'll just say it's register equals register ORed with the mask. Now, when I say OR here, I mean OR. Here's an alternate way of doing it. In C, this is the shorthand. If you take a value and do the bar equals, that's the same as register equals register. It's this shorthand. This is a very popular way that I you usually see in source code. So just keep in mind that if you want to set bits, it's a bitwise OR. Now, what if I want to clear a bit? So for example, if I have this one, and this one, and I want it to go to a 0 and a 0. How do I get from there to there? Well, let's look at a mask. I said a mask is a number where we set a 1, in the place where we want to do the bit operation. So how do we get from a 1 and a 1 to a 0? Well, you can think about subtract. That kind of works, but the problem with subtract is that if you subtract a 0 and let's say this is a 1, you generate a borrow, and that's not going to work. We're going to have the same problem as adding a 1 and a 1 with the carry. So I'll put a 0 back here. So let's think about bitwise. Maybe we did OR before. The opposite of OR is an AND. So 1 and 1 is 0. Okay, that doesn't work. Well, let me do one thing to the mask. Before, let me just alter it. Let me invert the mask. All right, let's try that AND again. 1 and 1 is 1. 0 and 1 is 0. Okay, that works. 1 and 0 is 0. Okay, that did clear the bit. 1 through to 0. Okay, that cleared it. All right, 1 and 1 goes to 1. All right, so it looks like if we do a bitwise AND on the inverse of the mask, we get what we want. So the other thing to notice is that everywhere we have a 1, it makes it look like we're just passing the data straight through the mask. Where we have a 0, it does not come through the mask. All right. So if we look at the C code, it's actually pretty simple. Just like the setting of the bits, we just do a register equals register. Ampersand is the bitwise and the tilde is the inverse. So we take the inverse of the mask and AND it with the current value to get our new value. The kind of other way you do the shorthand in C is ampersand equals is the same as saying register equals register AND. So the idea is we want a bitwise AND with the inverse, of the mask to clear bits. All right, so that's pretty simple. Now, what about toggling? So this is an interesting example. Now, I'm not going to go through the complete analysis, but I'm going to clue you in here, and you can kind of do this offline. What if you want to go from a 1 to a 0 or a 0 to a 1? You just want to flip the bit. So a good idea is blink the LED. So every time you come through the loop, you just want to blink it. You don't want to read its current state and say, is it 1 and go to 0? What logic operation is that? I want you to think about that maybe for a minute as I'm talking. So AND doesn't work, OR doesn't work. What logic operation would that be? All right. Now, I'll give you a clue. The logic operation looks like that in C, the little hat. So you go look that up, all right, and that toggles a bit. And you'll be able to use the same operator, with the mask. You don't have to invert, but figure out what that is and see if it works. All right, so that'll be your homework. Now, a note about masks. All right, consider this mask. Okay, we have a mask with bits 4 and 5 set. All right, this has a decimal value of 48 and a hex value of 30. Now, I'm not as good at looking at decimals on hex. I can kind of imagine what bits are set, in a mask if with a hex number. But if they get really complex with 3 or 4 bits, I got to think about it. Well, the good news is you don't really have to. We can let the compiler do the C compiler do the work. So let's think about this concept of can we decompose a mask into two simpler masks? So let's look at mask 1, where I have bit 5 set, and mask 2 with bit 4 set. All right. If we simply bitwise OR the mask, we get a new mask, a mask 3 that has the composite, both those bits set. So when you think about masks and you're making your own masks, kind of the convention most people use is you don't define composite masks. You define single bit masks, and then you OR them together. Because the reality is, when you do something like this in the compiler, it doesn't do this in real time. It doesn't actually compile it to code. It says, well, this is a constant, this is a constant. It ORs them together, during compile time, and generates that composite mask for you. So in C code, we could define a macro. If you don't know it, pound define. It simply takes this text and replaces it with this number. All right. So let's say we wanted to set bits 4 and 5. We can make a composite mask of 0x30, but we can also just OR our masks together and do our bit manipulation. The only caveat here is you always want to OR the uninverted masks in the case of a clear operation. So you notice I have it in parentheses here. All right. So that way you can kind of see what individual bits are in that mask. That's a very common thing to do. You'll see, in kind of industry code. Now, when we define masks, we can define it as hex. It's easy for me to see, what the hex is. Decimal, it's not quite as easy, but this one initially looks goofy, but it turns out this is, my preferred way of doing a mask. Now, what this operator is, in case you've never seen it in a class before, this is the bit shift operator. It says take this number, in this case 1, shift it to the left by 4 bits. All right? 1 shifted to the left by 4 bits. All right? That makes perfect sense. That's what a 1 is up here. It's a 1 shifted to the left by 4 bits. Well, let's look at that. So let's take the value 1. All right? And if we simply shift over that 1, we end up with a 1 here. So this is the same as a 0x10, all right, or a 32, all right? But the reason I like this notation is that, this is bit 4 is set with a 1, all right? So we need the 1 there to, that's like saying, okay, we have a bit, and we shift it to the left by 4 places, all right? So, now that's kind of an interesting way of doing masks, one last topic before we get back to the warp drive controller, is on bit testing. What if instead of setting or clearing bits, we wanted to see if a bit is set or not in a register? Well, it's pretty simple. Define a bit mask with the bit you want to test, and then do a logical AND, not on the inverse of the mask, with the mask. If the bit is set, you'll end up with all zeros everywhere else except in the placeholder where the bit, your original bit you were checking. Because remember, with AND, we need a 1 here for the original numbers to pass through. All right? And then simply ask, is the result greater than 0? All right? It's as simple as that. Now, in this case, the bit isn't set. And we check with our mask, and we say, is the result equal to 0? All right, there's another C shorthand, but for now we're just going to look at equals. Now in C, to test equality, you need the 2 sets of equal signs. So let's say we have a bit here at bit 4 and one at bit 5. If we want to see if bit 4 is set, we simply AND register and mask 1 and say, is it greater than 0? If register ANDed with mask 1 is greater than 0. If bit 4 is set, we can kind of, do something goofy in here. If we want to test, maybe we want to do something if a bit is clear. So in this case, we're going to AND mask 2 with a register and see if bit 5 is clear. And this will result in a value of 0 if it's clear. So let's go back to the warp drive unit, all right, and make some masks. So if I was writing a driver, a header file, which we'll look at in more detail in future videos, I would do something like this. I would define nice mnemonics where I'd put the register name, underscore, then the name of the bit, and then I would define the mask. Now you notice the notation I use. I like the 1 left shift by the bit the bit location you want it. You don't have to. You could use hexadecimal or decimal. I prefer, and you'll find that a lot of programmers prefer this notation. So all I do is I simply have all these defines, and I include that in my C file. And then we go to write code. So if we kind of remember our process before, we first have to make sure the warp drive is disabled. So we set the disable bit. Remember, setting is ORing. All right. We're going to set warp factor equals 82. All right. Next, we got to start the dilithium reaction. That was in our list. So I'm going to set the bit for enabling the dilithium reactor. And the next in the list was, it told us we have to wait until the bit is set. The dilithium reaction started is set. So I'm going to use a while loop and say while the register ended with the bit mask is 0, just kind of sit here and do nothing. We kind of got a loop. So it's just the CPU is going to sit here and pull in this loop right here until it's a 1. All right, once that's set, we know that's ready. The dilithium's ready. We can pre-charge the plasma. We do it by setting the plasma pre-charge bit. Once again, I'm going to test the plasma pre-charge complete bit until it's done. That's all this while loop is doing. All right. And lastly, in our step, we have to enable the plasma relay. So I'm going to set the bit for the plasma relay. And once again, I'm going to pull, that's a word, and wait until this bit is not equal to 0. If it's not equal to 0, that means it's greater. So we look at the WStat register, and get the mask in question. And you notice by using those nice mnemonics, we can kind of make the code more readable. If we used absolute addresses and the actual bit masks, someone else coming to read this would have a harder time reading it. So we want to definitely use some sort of mnemonic with a define. Now, lastly, we want to engage warp. Well, we use the warp engage bit, so we do the OR. And later on, we might want to look at the warp condition code. And notice I do something like this. I can right shift. If you remember before, the upper 4 bits of the WStat register was used for the status. So I'm going to shift them down by 4 so we get numbers between 0 and 15. And then here I just used a case statement to look at the different values. If you don't know what a switch case is, don't worry. You can look it up on Wikipedia or in the C book I prescribed earlier. Figure it out. So we're going to look at this more in later videos, but I just wanted to get you a feel for how you program hardware. It's all about testing bits, setting bits, and clearing bits. So some parting thoughts. This is all there is. Once you kind of learn this technique, you can write a driver. It's all about learning enough about C to be able to manipulate bits, implement maybe some state machines or write some sequences, and kind of be able to understand how to read a manual. All right. Here's another important point. I showed you on purpose how to do bit manipulation with standard C syntax. This is guaranteed to work on any hardware with any ANSI C compiler. Unfortunately, if you use another high-level language, and there's even some, I call them C-like compilers like the Arduino, I think Microchip, there's a compiler set called CCS where they declare these weird bit types that aren't actually ANSI C that only work with that compiler. I like using techniques that'll work with any compiler. And I can guarantee you with this method, it'll work. Now, it's up to you to read the hardware reference manual. Now, lastly, you might say, well, what if I do have an actual, what if my controller has a bit set instruction? You think about what this is doing. I'm reading the state of the bit, I'm ORing some numeric value with the register, then dumping it back. That sounds like 3 or 4 operations. Well, the good news is, since we have a compiler, a smart compiler, if it has a bit set instruction, almost all compilers now will look at this ORing and ANDing and know you're trying to set and clear bits, and it will try to optimize for that case. So this is, when I say this is industry standard nomenclature, you learn this way and you can program anything and look at anything. All right. So this is going to kind of conclude our hardware interfacing concepts. I hope this was helpful, and I hope it was fun. So from here, we're going to start looking at, real C code, real hardware, to kind of get a feel for, how do we actually make things work, with a real microprocessor. But I hope this initial series kind of got you kind of demystified what's actually going under the hood, because it's really not that complex, once you get it. So, good luck, and I'll see you in another video.